I'm Peter Davies, and I'm going to be talking about component stability in low-space massively parallel computation, joint work with Artur Cumai and Murad Parta. So the massively parallel computation model, MPC, is a parallel computation model. It's graph-based, so we have some giant graph on n nodes. M edge is a maximum degree delta. We're going to try and solve some problem on this graph, and we'll do so by applying a bunch of parallel processes to it. And the main restriction on these parallel processes are going to be that they have some bound S on the space. Okay, and we're interested particularly in the low space MPC model, which means that this bound S is some polynomial which is sublinear in n, so n to the epsilon for some arbitrarily small constant epsilon. Okay, the number of machines we're going to assume that we have is going to depend on whether we're looking at upper and lower bounds. We want to make the strongest possible choices in both cases. So with a couple of exceptions, the upper bounds in our paper are going to use somewhere pretty close to the optimum. The minimum number of machines we could use would be enough that we can fit the entire input into their total space. So total space, I just mean summing up the S space over all the machines. So the minimum we could use would be n plus m total space. And most of our upper bounds use n to the 1 plus epsilon plus m total space or lower, which is pretty close to optimal. And for the lower bounds that we're going to be talking about, they're going to be against algorithms that use any polynomial number of machines. So even ones that use quite large amounts of total space as long as it's polynomial. So this is the strongest case for both upper and lower bounds. Okay, so what happens when we run an MPC algorithm? Well, we take our input graph and we assume it's arbitrarily partitioned among the machines to begin with. Then each of these machines can do some local computation on the data they currently hold. And then there's a communication round where they send data to other machines. And we proceed with the synchronous communication rounds. The only restriction here is the space-bound S. So we are assuming that the computation done by the machines has to use no more than S space, and also the total amount of information they send and receive during the communication phases is also bounded by S. And as long as we observe that restriction, our goal is then to minimize the total number of communication rounds until we solve the problem, and we can output the solution to whatever problem we were trying to solve on the graph. So that's the MPC model. I'll also talk briefly about the local model, which is probably more familiar because we're going to see some connections between the two models in this talk. So the local model, again, we have an input graph, n nodes, m edges, maximum degree delta. But now, rather than applying a bunch of parallel machines to solve a problem on this graph, the computation is actually done by the nodes of the graph. So there's some kind of connection between the spatial positions on the graph and the computations and the information they start with. So again, we proceed in synchronous rounds. And now we don't have any space bound or anything, so the local computation is unbounded, and we can send arbitrary messages to the neighbors in each round. So really, it's only the locality that matters here. And again, we want to know what's the minimum number of rounds we need in order to solve our particular graph problem. Okay, so what's the connection between these two models? Well, we can simulate local algorithms in MPC, and actually we can do so very quickly using a procedure known as graph exponentiation. So I'll explain what that is and how we do it. The first thing is the observation that a T-round local algorithm is equivalent to a process where you can just show each node its T-radius neighborhood, and then it should be able to decide what its output should be based on that information immediately. Okay, and there's a well-known equivalence between that and a T-round local algorithm. So what our MPC algorithm can do is try to collect these T-radius neighborhoods onto single machines, and then that single machine can determine the output for a node. Okay, and to do this, we need that these T-radius neighborhoods actually fit into the space of a machine, smaller than the space-bound S. This seems like a major restriction, and in some cases it is, but actually in the context of this work, we can basically ignore this because all the interesting stuff happens in the low degree regime where this is pretty much always the case, or we can make it the case. So even though this might seem like a very special case, actually, you can ignore this for the purposes of this talk. So how do we get these radii onto machines quickly? We start off with a node, we dedicate it a machine, and then we can find out what are its neighbors. The edges for this node have to be stored somewhere, and we can sort them and do some communication primitives so that we can get them in constant rounds onto our machine. Assuming we've done that for all nodes, we can now query each of the nodes we have in memory that are distance 1 away from our dedicated node and ask for their 1-hop neighborhoods. And combining these all together, we get the node's 2-hop neighborhood. Okay, and then we can repeat this process. Assume we have 2-hop neighborhoods for all the nodes given on their dedicated machines. We can now query all the 2-hop neighbors, ask for their 2-hop neighborhoods, combine them together, we get 4-hop neighborhoods. Okay, so after only log t many iterations of this, we can get the t radius neighborhood onto a single machine. And then we can determine the output for this node using our local algorithm as a black box. Okay, so using graph exponentiation, under these circumstances, we can simulate local algorithms at an exponential speedup in low space MPC. Okay, to complement that, there was a very nice recent result by Ghaffari, Kuhn, and Rito that showed that we can do a similar thing by taking local lower bounds and bringing them over to low space MPC, again at an exponential speedup, so a log factor of what the original lower bound was. So there's this Mutable Theorem here, which I've slightly paraphrased. There are some more details that I'm skipping. I'll refer to this as GKU because I'm going to refer to it a lot. And essentially what it says is the following. We have some graph problem P that we're trying to solve. Assume that we have a T of n lower bound in local, so randomized local, and in fact using shared randomness, but that's not going to be important to us here. And we need that this T is at most logarithmic, but that's the case for most local lower bounds. And then if we can do better than log of this in low space MPC, so better than we could do by graph exponentiation, then we can solve a problem that's assumed to be very difficult in MPC, which is this connectivity problem of distinguishing a single n node cycle from 2 different n/2 node cycles in less than logarithmic time. And people spent a lot of time trying to solve this when MPC first came about, and they didn't solve it. And for that reason, it's conjectured to be hard. It's conjectured that you can't solve it quicker than log n. There are results showing that under our current understanding of complexity, we can't hope for unconditional MPC lower bounds. So given that we need a condition, this is the condition that's being used. So when we say conditional lower bounds, we mean assuming that you can't solve this connectivity problem fast, which is a conjecture that people generally believe. Okay, so given a local lower bound, we can get a conditional MPC lower bound that's the log of the local lower bound, is essentially what GKU is saying. And in this work, we focused on one particular part of this theorem that isn't yet really defined, which is this component stability term here. So what does component stability mean? Well, informally, it means that we have a node here. Our algorithm should determine this node's output based only on its connected component and the randomness. Okay, so excluding the other connected components of the graph. If they change, it shouldn't change our output for this node here. And at the time of GKU, and there's a statement in GKU saying that all known MPC algorithms were thought to be component stable, or you could easily make them component stable. Okay, so at the time of GKU, it appeared that component stability was only a kind of technical triviality, and this covered all MPC algorithms. Okay, so now we're up to where we came in, and we have 4 main points that we want to show about component stability. The first is that you actually have to be very careful about this concept of component stability. So it's actually a very fragile concept, and we show that it needs some tweaks to actually incorporate most existing MPC algorithms. And you need to be very careful about exactly how you define it, because small changes in the definition can have worrying implications depending on what results you're aiming to get out of it. So that's the first thing. The second thing is that the framework of GKU can be extended not just to randomized algorithms that depend on n, but also to deterministic lower bounds and lower bounds that have dependency on the maximum degree delta as well as n. And that actually covers most local lower bounds. So we can extend it basically to be able to lift almost any local lower bound to MPC. The third thing is to show that rather than being just a technical triviality that doesn't really matter, actually component stability does restrict the power of MPC. So while we can get these conditional lower bounds against component stable algorithms, in some cases we can show that there are faster algorithms that aren't component stable, that beat the lower bounds. Okay, so just because you get a lower bound out of this framework doesn't mean you should give up. It may well be the case that you can beat the lower bound, and in fact, for deterministic algorithms, it's very often the case. So the component stability is a severe restriction on the power, particularly of deterministic algorithms. So I'll start with the first point. So caution when defining component stability. What's the problem with the component stability definition I informally gave earlier? Well, if you look at prior MPC algorithms that were assumed to be component stable, the output of a node there generally depended on its connected component and the randomness, which is fine, but also the value of n, and even the exact value of n, because unlike in the local model, where we assume often that we're given some input estimate of n, because otherwise we have no way of actually finding out any estimate of n at all. We have to be given it as input. In MPC, you can immediately, at the start of any procedure, find the exact value of n in constant bounds, and then you can use it. Okay, so in MPC, we should always assume we have access to the exact value of n, and our algorithms would naturally use it. So if you want to define component stability in a way that actually includes known and natural MPC algorithms, you have to allow dependency on the exact value of n, right? And this causes some problems for the framework of GKU. And in fact, we show that it should cause some problems with the framework of GKU, because actually you can't hope to get a result of the kind I just showed you, the theorem I showed you, using a definition of component stability that allows dependency on n and thereby actually includes most MPC algorithms. So here's an example problem. The problem is a decision problem to answer yes if your graph is a single simple path with consecutive IDs, and no if it isn't. Okay, this has a trivial local lower bound because you can't possibly hope to do this in less than n-1 rounds. The reason being that if you have something that's a single simple path with consecutive IDs, and then you tweak one of the endpoint's IDs, the answer changes from yes to no. And the other endpoint can't determine this in less than n-1 rounds of local. So you trivially can't solve this problem in less than n-1 rounds of local. You can solve it in constant rounds of MPC, low space MPC, by basically just checking that everyone's degrees and the IDs of their neighbors agrees with them being part of a single simple path with consecutive IDs. Okay, so therefore we can't possibly hope for a theorem of the kind I just showed you, because there's no way we can take any of the possible lower bounds on this problem in local and turn them into anything non-trivial in MPC. So that's a problem, but actually we show that by making some tweaks to the definitions, using the framework, adding some new concepts, and accordingly changing the proofs, we can essentially recover the result of GKU and provide a framework that, while it doesn't give a lower bound lifting result for all problems, it gives a result for a very wide class of problems that includes basically all the problems we care about. And by doing so, we then recover all the applications of GKU, including these. Okay, so yeah, we show essentially that you need to be very careful about component stability, but that you can follow the very nice reduction framework of GKU as long as you make some tweaks to the definitions and proofs. Okay, while doing so, we make some extensions to the framework. So we also extend it to allow deterministic lower bounds and lower bounds that depend on the maximum degree. And I'll just list some of the deterministic lower bounds we get as a result of this. So for example, we can get deterministic lower bounds for maximal independent set and maximal matching based on a very nice recent paper of Valio et al. In the local model. And also we can get lower bounds for problems related to the lowest local lemma and degree splitting, such as synchronous orientation, delta vertex coloring, 2 delta minus 2 edge coloring, and those apply even in forests. Okay, so on to the third and fourth points, which are showing that component stability isn't just a technical triviality and actually significantly restricts the power of the low space MPC model. So first, I'm going to show an example problem where we have a randomized algorithm that's not component stable that surpasses the component stable lower bound. And this problem is fairly natural. It's just defined an independent set of size omega of n over delta, so a reasonably large independent set. And if you are familiar with Luby's algorithm, you might notice with a bit of thought that there's a very simple MPC algorithm that does this in expectation. So if you just run one round of Luby's algorithm, then you'll actually get a independent set which is of size order of n over delta in expectation, and therefore succeeds with constant probability. We want a randomized algorithm that succeeds with high probability, but in MPC this is quite easy to get. So what we do to get from constant to high probability is we just run a logarithmic number of concurrent versions of this one round of Luby's algorithm and pick one that does indeed give us an independent set of the appropriate size, which we can easily count. Okay, and because these independently succeed with constant probability, the whole thing succeeds with high probability. And in fact, we show that with a bit more work, you could de-randomize this and get a deterministic constant round algorithm for the same problem. But we can also apply our framework to a recent result and get a conditional lower bound for component stable algorithms on the same problem of log star n. Okay, it's pretty low, but it's not constant. So we can show using this recent result of Kawara-Bayashi et al. That component stable algorithms can't do better than log star n, but a simple component unstable algorithm, even deterministic, can get constant rounds. So the upshot is that component stability is a restriction on randomized algorithms. And the reason for this, the place we're using component instability to help here, is this step, running concurrent versions of an algorithm and agreeing on one that succeeds. And this is a version of a technique which is often called success probability amplification. It's quite commonly used, and it's inherently component unstable because we're running a bunch of different versions of some process, and we're picking one based on some global success criteria. And the one we pick defines our outputs for all of the nodes, regardless of the connected components. So the whole process is completely component unstable. And that's what's giving us extra power here to surpass the lower bound. And this is even more pronounced for deterministic algorithms. So actually, we show that many standard de-randomization techniques are, again, inherently component unstable. They're doing similar things to what I just showed you. And by doing so, we get separations for all of these problems and probably many others, where we can show component stable lower bounds, conditional lower bounds, and we can surpass them with component unstable algorithms. And these are just using standard de-randomization techniques that have been used to good effect recently, such as spanner independence hash functions or pseudorandom generators under the method of conditional expectations. And in fact, even very simple algorithms can break these component stable lower bounds. So the moral here is that component stability significantly helps, usually helps, in fact, in deterministic algorithms for low space MPC. So I'll just go back to our main points to take away. Firstly, that you need to take a lot of care when defining and working with component stability. But secondly, that we can get the framework to give us robust bounds that do incorporate all known existing, or almost all known existing MPC algorithms. And we can extend them to work for deterministic bounds, bounds that depend on delta. But we can show examples where you can break these lower bounds using component unstable algorithms. So you shouldn't necessarily think of these lower bounds as final. You can often get around them with component instability. So that's all I wanted to say. So thank you for now, and hopefully I'll see you at the live talk to answer any questions. Thank you.